Hey, today I'd like to talk about modeling and optimization. What you're going to learn about in this lesson is how to use derivatives for practical applications in finding maximums and minimum values in business, economics, and math contexts. So you might ask yourself, what is optimization? Well, if you can define a problem in such a way that you're relating two variables, then we could find the maximum and minimum values in the situation, just like we've been doing with any function. So examples of ways we could use this, we might maximize area if we're given perimeter. We might maximize profit when we're given the cost of production. A biggie is to maximize volume or minimize surface area. There's lots of different ways we can use this. Now, when we do this type of thing, what we're going to do, start first, is we're going to follow these steps. First, we want to understand the problem. What do we want to find out? What information do we have that we can use? Then, we're going to develop a mathematical model. We'll draw and label pictures a lot of times. We'll usually write two equations. One of the equations will give us a way to get, it'll be our restraint, and the second will be, or constraint, and one will be the equation we're going to use to find a maximum or a minimum value. And what we do is we use substitution to get two variables in that equation before we max or minimize it. If possible, we're going to graph the function because it's real easy to find a maximum value or a minimum value. Be sure that when we do that, we look at a reasonable domain for the function and don't find max or min values outside of that domain. Now remember, when we graph the function, it'll give us an idea, but a lot of times we can't use a calculator, or when we do use it, it's only to see if we're right. You know, we're talking about using our analytical skills in these cases. So we will find our derivative to find the critical points and the endpoints, and we'll use our first or second derivative test to see if we have a max or a minimum value. The last step, of course, will be to answer our question, to interpret the solution, writing it as a sentence, making sure we use units where applicable so that we have something that makes sense when we do it. Let's look at a very simple example to start with. Okay. What we're going to do here is we're going to find two non-negative numbers whose sum is 20 and whose product is as large as possible. So step one, we want to understand the problem. We need two numbers. Let's call them x and y. Okay? And those two numbers, when we add them together, they need to equal 20. Now, when we multiply them, the product, that's what we want to maximize. So that's what we want to find the largest product possible. Now, when we do this, we know we can't maximize something with two variables to it. So what we're going to do is I can take this, my constraint, and say, well, instead of putting y down here, I'm going to call this, I'm going to say that y equals 20 minus x. Because that way, I take this, put it in here, and I get an equation that I can easily maximize. Because now I can say f of x, what I'm going to maximize, is equal to x times 20 minus x. Okay, so now that one I can maximize. That would give me the largest possible product. To do this, we're just going to go through that same process we've been doing using either the first or the second derivative test. Well, I don't want to use the product rule, so I'm going to simplify this first. Get 20x minus x squared. Now I'll take my derivative. 20 minus 2x. And if I set that equal to 0, take away or add 2x to both sides, and x equals 10. Now, the thing is, I need to know if that's going to be, so we have here a critical point. It might be a max, it might be a minimum. We're hoping it's a maximum, but what we'll do to verify this is we'll take the second derivative. And if f prime is 20 minus 2x, the second derivative is just negative 2. Well, when I verify this, I know that if f double prime is negative, f of x is concave down, and x equals 10 is a max by the second derivative test. Now I need to find two numbers, x and y. Well, I know from up here that x plus y equals 20, so y must equal 20 minus x. So I know x equals 10 is a maximum value, and at that value y equals 20 minus x, so that gives us 20 minus 10, which is also 10. Now so the two numbers were the sum of 20 and the maximum product are 10 and 10. Now, if I just did a little monkeying around to try a few numbers out, I might say, what about 11 times 9? When you add that together, it equals 20. When you multiply it, it's 99, less than 100. What if I did 12 times 8? Well, 12 plus 8 is 20, so I'm still satisfying this constraint. When I multiply this together, 8 times 2 is 16, carry the 1, 96. Notice, and over here, the maximum product is 100. So notice these products are last couple numbers just to check. So that's our basic strategy. We want to figure out what we're looking for, write an equation with a constraint and another equation to maximize what we're trying to find. We're going to analyze the equations. We'll take the first derivative to find our critical point. Easy way to do it is to take the second derivative to see if that critical point is a max or a min. Of course, you could use the first derivative test also. And then make sure you say what you found. Interpret your solution. And maybe try a few other points just to make sure that you're right. I want to look at one more here, and then we're going to, I think that'll be it for this video. Now here, we're going to look at inscribing rectangles, and our problem is we've got a rectangle that needs to be inscribed under one arc of y equals the sine of x. We want to know what is the largest area the rectangle can have, and what dimensions give that area. Well, again, we want to see first, understand the problem. So right here, I'm graphing y equals the sine of x. It's this nice arc here. This goes from 0 to pi, and I sketched it over here too. So what I can see is I want to inscribe a rectangle inside of it with the greatest possible area. Now, to do that, I need a length and a width, because area of a rectangle is length times width. Well, my length, I see whatever this length is x. That's going to be taken away from this overall thing. And because of the symmetry of the pi function, it's going to be 2x. So for this length, I could call this pi minus x, or pi minus 2x. Okay? Now the height of the rectangle, no matter what I take for x, the height's just going to be f of x, which in this case is the sine of x. So my area function that I'm going to maximize is going to be pi minus 2x times the sine of x. Now at this point, we look at that, and I can tell you right now, when you've got something that's more of a linear function and you're multiplying it to a trig function, there's no way to analytically solve this. So if you can see this is the case, then you have a nice simple problem, and we're going to calculate our maximum, because we want the maximum, we don't want the maximum of this. We want to take the maximum of the function we just wrote. So I'm going to turn this off and look at the function we just wrote. And we need this value right here. So we'll calculate the max. And that's going to tell us the x value that would give us the largest area for our rectangle. And I see that x value is 0.710. So I've got a of x. I'm going to calc the max. That's what I did. And x is approximately equal to 0.710. Now at this point, I'm going to go, I've got x, 0.710, and I'm going to store that as a. Because what I want to be able to do, and if you looked at this, it makes a lot of sense. That's saying that right here, if I make my rectangle right here, that's going to get the highest area. Now, for my verification, while I calc max, that's all you can do in this case. When I interpret that, that means the length of the rectangle is pi minus 2x. So I'll do pi minus 2 times 0.710. And I stored that. So I'll just say pi minus 2 times a, and my length is 1.721. Now my height, or the width of the rectangle, has to be the sine of x, so I'm going to call up the sine of 0.710. So I've got the sine of a, because I stored it, and that's 0.652. So there's my maximum. To get the maximum area, length is this, width is this, and the area is, and now to get my area, I'm just going to multiply. I've got 0.652, so I'm going to say, I'll do this, 1.72066549, because I'd like a lot of accuracy, times the answer. And my area is 1.122 square units. So maximum area will happen when when x is approximately 0.710, the length is 1.721 units, the width is 0.652 units, and the area is 1.122 units squared. So that's the first part of this, and part B will include a few more examples. Thank you.